Good morning, I'm Manuel Zarzo. We are in Unit 8, Regression, and today I will present the theoretical model of regression. Okay, so imagine that we have this. We have x, which is the explicative variable. We have the y, which is the dependent variable. This is the marginal distribution of the y that we assume that it's normal. So approximately here we would have the minimum value. This would be the maximum value, and then this would be the average. And then we have some different conditional distributions. Okay, so if we focus on the values of x1, so this would be the conditional distribution. This would be the conditional distribution of the y focused on values x2 and x3. Okay, conditional distribution. So they have an average. The expectation of the y given a specific value x1 is m1. Okay, this is the same. The average of the y given a value x2 we will call m2, and so on. Okay, and then we have the regression line. The regression line crosses the average. Okay, so the conditional distribution of the y given a specific value of x is a random variable that is computed with this equation. Okay, the predicted value of the y, which means the expectation of the y given a specific value, is alpha plus beta multiplied by x. So this is the equation of the straight line. Beta is the slope, alpha is the ordinate. We use the Greek letters at the population level. It means that we are defining this straight line at the population level. Okay, so the linear relationship at the population level between two components of a bivariate random variable x and y. But usually what we have is data from a sample. Okay, so we will call a plus b multiplied x. So the slope will be called b, the ordinate will be called a, okay, because they are estimated values from the sample. Okay, there's a linear relationship estimated from the sample. So the best estimation for alpha, okay, so the ordinate at the population level, is the value obtained from the sample, and the best estimation of the slope at the population level is the slope that we have obtained from the sample. And then here another important thing is that the regression line predicts the average value, which is important. Okay, so here we have the regression line, and then this line predicts the average value. Okay, when we make a prediction, the prediction is for the average. Good. So this is a similar plot, but in 3D, 3 dimensions. We have the variable x, explicative variable. We have, and here this is the variable the y, the dependent variable, and then this would be like the density function. So we have the marginal distribution of the y, and here we have the conditional distributions of the conditional distribution of y for different values x. Okay, conditional distribution of y given different value x. Okay, marginal distribution, and then so here an important issue is that here we're plotting this 3 density function with the same size. Okay. So the variance of this 3 density function is the same, and then that is one of the hypotheses of the theoretical model. So the variance of the y for a particular value x, okay, so the variance of the conditional distribution of y is going to be constant, and we will call that residual variance, okay, because if we compute the residuals and then we compute the variance of the residuals, that is actually the value. So it is very important that in this model we were assuming that this variance is constant, and this is called hypothesis of homoscedasticity. This is a strange word. This is the first time that I present the word. Homo in Greek means equal, and when the variances are different we call it heteroscedasticity. Hetero in Greek means different. Okay. Then, by definition, okay, this definition appeared also in previous videos. Residual, by definition, is a value observed minus a value predicted by the model. Usually, the best prediction is an average. Okay, so the residual from observation is the value of the y observed minus the prediction, in this case given by the straight line. Okay, so we substitute x in the equation of the straight line, and then that gives me a prediction. So we make the difference, and that is the residual. Okay, so if I compute the variance of all residuals, that is here, that is the value, that is the variance of the conditional distribution of the y. So residuals will follow a normal distribution, the average is 0, and we assume that they are constant. They don't depend on x. Okay, variance of the residuals, or also called residual variance. Okay, important, remember the variance of the conditional distribution is the variance of the residuals. That is an important equation. And this is less than the variance of the marginal distribution of the y, as we can see in this picture. Good. So now, imagine that we have data. So now let's discuss this with data. Imagine that I have data x, x and y. Okay, so it could be like gas consumption for heating in winter. And then we have for the different days, x would be the temperature, the mean temperature of the day. The y would be the response variable, and the x is the predictive or explicative variable. Then we make a plot of the y versus x, and this is what we have. We have a negative correlation. It means that when x increases, the y also tends to increase. So we can see that there's a clearly, we can fit a straight line that will give us more or less a good estimation, a good prediction. Okay, so we will fit a line y equal a plus b multiplied by x, where b is the slope and a is the ordinate. Okay, so if the temperature in one day is 12, we will substitute 12 in the equation of the line, and then we will make the prediction. Okay, this is the resulting values for the fitted equation. Okay, the slope and the ordinate. Okay, and remember that the fitted model predicts the mean. It is very important. If one day the temperature is 12, it does not mean necessarily that the gas consumption will be 34. I will have 34 will be the average. Okay, I can compute an interval, more or less like here, but the prediction is the average. Good. So I can apply this equation that we have obtained with the star graphics, and then we will have the predicted value. Okay, the predicted value. So I take every value x, this value goes here, I multiply by the slope, and I add the constant, and then I get the prediction. And next, making observed value minus predicted value, I'm getting the residuals. So these are the column, this is the column of the residuals. Value observed minus value predicted. Okay, the sum of the residuals and the average of the residuals is always 0. Okay, residual is the error of the model. It accounts for the effect of all the remaining factors not included in the model. And this is true for ANOVA and regression. Always the average of the residuals is 0. But the hypothesis is that we assume that residuals are normal and they are independent. Okay, that is important. This is the hypothesis of the model. Then regression. Regression is a statistical method that we can apply to establish a model. A model is a mathematical equation that we can use to predict one dependent variable as a function of one or more input variables. These input variables sometimes are called predictors, or predictive variables, or explicative variables. So if the y is a function of just one single x, it is called simple regression. If the y is a function of more than one x, it is called multiple regression. And we have two types. We can have linear multiple regression, or we can have non-linear multiple regression. In this subject, we will just explain linear multiple regression. We don't have, this is out of the scope, the non-linear regression is out of the scope of this subject. Okay, and then we can have an empirical model, or we can have a deterministic model. The models that we deal with in statistics are called empirical. Empirical means based on observed data. For example, we can predict the weight of a person as a function of the height. Okay, we can get an equation like this, but always we will have an error. Okay, so the prediction is not 100% accurate. There is an error. It accounts for all causes of variability. So we say that there is a partial uncertainty. So the prediction is not 100% when we apply the equation, becomes some kind of uncertainty. Empirical models don't always reflect cause-effect relationships. This is something that I will explain later on. But in physics, we have different kinds of equations. They're called deterministic models, like the force or like strength equal mass multiplied by acceleration, or the Einstein equation, or many others. So all equations of physics, we never see plus an error. Okay, we are not used to that. Okay, so the uncertainty is null. It means that when we apply the formula, we assume that the prediction is 100% accurate. Okay, that is what we would assume always that we apply a physics equation. So these kind of deterministic models model causality. So these models express cause-effect relationships. Okay, I will discuss this issue in another slide. So analysis of residuals. So we recommend to represent always the residuals on a normal probability plot. Okay, it is useful to detect outliers. Okay, if we're sure that one or more values are outliers, we should remove them from the analysis. For example, in this case, okay, we can see how these values clearly separated from the rest. So we can fit a straight line, but we can see that this value clearly separates from the straight line. So that would be an outlier. And then the analysis should be repeated after discarding the value, because this value affects the slope, affects the ordinate, and affects the significance of the parameters. So always that we're sure that a value or more than a value are outliers that don't belong to the population, they should be discarded and the analysis should be repeated. Okay, because just one single outlier can be responsible of part of the results. Okay, and also at the same time, the normal probability plot is useful to detect lack of normality in the data. In case of a positive skew, we should apply transformations. For example, the square root, the fourth root, or the logarithm. Okay, and also it can be useful to detect lack of linearity in the relationship between x and y. Okay, this can be studied just by representing the residuals as a function of x. And then this is an example. Here we can see that the residuals as a function of x more or less follow a random pattern. Okay, so we don't see any kind of trend. And moreover, another important thing is that the variability of the residuals is more or less constant. Okay, because that is another hypothesis of the model. Remember that hypothesis was called homoscedasticity. The variance of the residual is constant, it does not depend on x. So here, approximately, we can see that this variability does not depend on x. So we can see graphically that the hypothesis of homoscedasticity makes sense. But this would be a different case. Here, we can see a trend. The residuals, when x is low, most of the residuals tend to be positive. When x take a central value, most of them tend to be negative, and then at the end also most of them tend to be positive. So here we can find a trend like that, and this is an indication that there is a quadratic relationship. So the analysis of residual has provided us with this interesting piece of information. Okay, and here I finish this video about the theoretical model of regression.